The inspector's requirement for a second ground rod is based on the National Electrical Code, specifically NEC section 250.53 A2. This section states where multiple grounding electrodes are used, they shall be spaced not less than 6 feet or 1.83 meters apart. The NEC does not specify a specific distance of 8 feet, but the inspector may be requiring this based on local practice or soil conditions. Multiple ground rods increase the overall grounding reliability by providing redundant paths for fault currents. If one ground rod fails, the other rod or rods can still provide a low resistance grounding path. This improves safety by reducing the chance of electrical shock or fire in the event of a ground fault. The ground rod should be at least 8 feet long and driven into the ground to a depth of not less than 6 feet. The ground rods should be connected to each other using a copper bonding conductor. The bonding conductor should be installed underground and protected from damage. Where soil conditions make it difficult to achieve a low resistance ground, additional ground rods may be required to meet the required grounding resistance. Considering these points ensures a safer and more compliant electrical service installation. When upgrading an electrical service, proper grounding is crucial for safety and compliance. The NEC provides guidelines for grounding electrode systems to ensure effective fault current paths and minimize the risk of electrical hazards. Firstly, the NEC section 250.53 A2 addresses the spacing requirements for multiple grounding electrodes, specifically ground rods. It mandates a minimum separation of 6 feet or 1.83 meters between ground rods. This spacing is intended to prevent the electrodes from interfering with each other's electrical fields and to ensure that each rod effectively dissipates fault current into the earth. Secondly, while the NEC specifies a minimum spacing, local inspectors may impose stricter requirements based on regional soil conditions or established practices. In areas with high soil resistivity, achieving a low impedance ground connection may necessitate greater spacing between ground rods or the installation of additional rods to meet the required grounding resistance. Such measures are aimed at enhancing the overall effectiveness of the grounding system and reducing the likelihood of electrical faults. Thirdly, the benefits of utilizing multiple ground rods in an electrical system are multifaceted. The most significant advantage is the redundancy they provide in the fault current pathway. In the event that one ground rod becomes compromised due to corrosion, damage, or poor soil contact, the remaining rod or rods can still provide a low impedance path to ground, ensuring continuous protection against electrical faults. Fourthly, multiple ground rods enhance the overall reliability and stability of the grounding system, particularly in environments prone to fluctuations in soil moisture content or seasonal variations. By distributing the grounding responsibility among multiple electrodes, the system becomes less susceptible to variations in soil resistivity and maintains a more consistent grounding impedance over time. Fifthly, in addition to spacing requirements, the NEC also specifies the minimum length and depth for ground rods. According to the code, ground rods must be at least 8 feet long and driven into the ground to a depth of not less than 6 feet. This ensures that the rod makes adequate contact with the surrounding soil and provides a sufficiently low impedance path to ground. Sixthly, proper bonding of ground rods is essential for creating an effective grounding system. The NEC requires that ground rods be connected to each other using a copper bonding conductor of appropriate size, typically based on the size of the service entrance conductors. This bonding conductor should be installed underground and protected from physical damage to maintain the integrity of the grounding system. Seventhly, the installation of a grounding electrode system should be performed in accordance with the manufacturer's instructions and relevant industry standards. It is important to use appropriate tools and techniques to drive the ground rods into the ground without damaging them. Additionally, the bonding connections between ground rods and conductors should be made securely and protected from corrosion to ensure long-term reliability. Eighthly, it is worth noting that the NEC does not specify a maximum number of ground rods that can be installed as part of a grounding electrode system. In situations where soil conditions are particularly challenging, it may be necessary to install multiple ground rods to achieve the desired grounding impedance. However, it is important to ensure that all ground rods are properly spaced, bonded, and installed in accordance with the code requirements. Ninthly, when upgrading an electrical service from 150 amps to 200 amps, it is crucial to reassess the adequacy of the existing grounding electrode system. The increased service capacity may necessitate the installation of additional ground rods or the upgrade of existing grounding conductors to ensure that the system can effectively handle potential fault currents. Tenthly, the use of supplemental grounding electrodes, such as ground plates or ground rings, can further enhance the effectiveness of the grounding system, particularly in areas with poor soil conductivity. These supplemental electrodes provide additional surface area for dissipating fault current and can help to reduce the overall grounding impedance of the system. 11thly, regular inspection and maintenance of the grounding electrode system are essential for ensuring its continued effectiveness. Ground rods and bonding conductors should be visually inspected for signs of corrosion, damage, or loose connections. Additionally, the grounding impedance of the system should be measured periodically to verify that it remains within acceptable limits. 12thly, in situations where plastic plumbing is used and a cold water ground is unavailable, the NEC requires the installation of an alternative grounding electrode system. This may include the use of ground rods, ground plates, or other approved grounding electrodes to provide a reliable path to ground for electrical faults. 13thly, when installing ground rods, it is important to avoid underground utilities and other obstructions. Before driving ground rods into the ground, it is recommended to contact local utility companies to locate any buried cables or pipes and to ensure that the installation does not pose a safety hazard. 14thly, the use of exothermic welding, also known as catwelding, is often recommended for making bonding connections between ground rods and conductors. Exothermic welding creates a permanent, low-resistance connection that is highly resistant to corrosion and mechanical stress, ensuring the long-term reliability of the grounding system. 15thly, in areas with rocky or otherwise difficult soil conditions, it may be necessary to use specialized techniques for installing ground rods. This may include the use of a ground rod driver or the installation of ground rods at an angle to penetrate the soil more effectively. 16thly, the NEC requires that all grounding electrodes be bonded together to form a unified grounding electrode system. This ensures that all parts of the electrical system are at the same potential and that fault currents have a clear path to ground. 17thly, when installing ground rods near concrete structures, it is important to avoid driving the rods through the concrete. This can damage the concrete and compromise the integrity of the grounding system. Instead, ground rods should be installed adjacent to the concrete structure and bonded to the reinforcing steel using an approved bonding method. 18thly, the NEC provides detailed requirements for the size and type of grounding conductors used to connect ground rods and other grounding electrodes. The size of the grounding conductor is typically based on the size of the service entrance conductors and must be sufficient to safely carry the maximum potential fault current. 19thly, when installing ground rods in corrosive soil environments, it is important to use corrosion-resistant materials and coatings to protect the rods from degradation. This may include the use of stainless steel ground rods or the application of a protective coating to the rods to prevent corrosion. 20thly, the NEC requires that all grounding connections be accessible for inspection and maintenance. This means that ground rods and bonding conductors should be located in areas where they can be easily inspected and accessed for repairs or replacements if necessary. 21stly, when upgrading an electrical service, it is important to consider the impact on the existing grounding electrode system. The increased service capacity may require the installation of additional ground rods or the upgrade of existing grounding conductors to ensure that the system can effectively handle potential fault currents. 22ndly, the NEC provides specific guidelines for the installation of grounding electrodes in various types of soil conditions. In areas with sandy soil, it may be necessary to use longer ground rods or to install multiple ground rods to achieve the desired grounding impedance. 23rdly, the use of ground enhancing compounds can help to improve the conductivity of the soil around ground rods, particularly in areas with poor soil conditions. These compounds can be applied to the soil before or after the installation of the ground rods to reduce the grounding impedance and enhance the effectiveness of the grounding system. 24thly, the NEC requires that all grounding electrodes be clearly identified and labeled. This helps to prevent accidental damage to the electrodes and ensures that they can be easily located for inspection and maintenance purposes. 25thly, when installing ground rods near underground pipelines, it is important to maintain a safe distance to prevent electrical interference or corrosion. The NEC provides specific guidelines for the separation of grounding electrodes from underground pipelines to minimize the risk of damage or interference. 26thly, the use of a ground resistance meter is essential for verifying the effectiveness of the grounding electrode system. A ground resistance meter measures the impedance between the grounding electrode and the surrounding earth, providing a quantitative assessment of the system's ability to dissipate fault current. 27thly, the NEC requires that all grounding connections be made using approved connectors and fittings. These connectors and fittings must be listed for the intended use and must be installed in accordance with the manufacturer's instructions. 28thly, when installing ground rods near trees, it is important to avoid damaging the tree roots. Tree roots can interfere with the effectiveness of the grounding electrode system and can also be damaged by the installation of ground rods. 29thly, the NEC provides specific guidelines for the installation of grounding electrodes in concrete encased electrodes, also known as UFA grounds. Concrete encased electrodes are typically used in new construction and provide a very effective means of grounding electrical systems. 30thly, the use of a ground fault circuit interrupter, or GFCI, is an important safety measure that can help to prevent electrical shocks and injuries. GFCIs are designed to detect ground faults and to quickly interrupt the flow of electricity, protecting people from electrical hazards. 31stly, the NEC requires that all metal enclosures and equipment be properly grounded to prevent electrical shocks and injuries. This includes metal boxes, conduit, and other metallic components of the electrical system. 32ndly, the use of a surge protective device, or SPD, can help to protect electrical equipment from damage caused by voltage surges. SPD are designed to divert surge current away from sensitive electronic equipment, preventing damage and prolonging the life of the equipment. 33rdly, the NEC provides specific guidelines for the installation of grounding electrodes in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present, and special precautions must be taken to prevent electrical sparks or arcs from igniting these substances. 34thly, the use of a lightning protection system can help to protect buildings and structures from damage caused by lightning strikes. Lightning protection systems are designed to safely conduct lightning current to ground, preventing damage to the building and its contents. 35thly, the NEC requires that all electrical work be performed by qualified and licensed electricians. This ensures that the work is performed safely and in accordance with the applicable codes and standards. 36thly, the use of a building's metal frame as a grounding electrode is permitted under certain conditions as outlined in the NEC. This requires careful bonding of the metal frame to the grounding system. 37thly, when dealing with existing buildings, it's crucial to assess the existing grounding system and ensure it meets current code requirements. This may involve upgrading the grounding system to accommodate the increased electrical load. 38thly, understanding the local amendments to the NEC is crucial, as local jurisdictions may have specific requirements that differ from the national code. 39thly, proper documentation of the grounding system is essential for future maintenance and inspections. This includes keeping records of the location of ground rods, bonding connections, and test results. 40thly, continuous education and training on grounding and bonding practices are crucial for electricians to stay up to date with the latest code requirements and best practices. 41stly, regular testing of the grounding system impedance is recommended to ensure it remains within acceptable limits. This can be performed using a ground impedance tester. 42ndly, in some cases, a driven ground rod may not be the most effective solution. Alternative methods like chemical ground rods or ground grids may be necessary. 43rdly, proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. By following the NEC guidelines and best practices, electricians can help to prevent electrical shocks, fires, and equipment damage. 44thly, the role of the electrical inspector is to verify that the grounding system complies with the NEC and local codes. It's important to cooperate with the inspector and address any concerns they may have. 45thly, ensuring all metal water pipes are adequately bonded to the grounding system is an important safety measure, even if the plumbing is primarily plastic. This helps to minimize the risk of electrical shock from metallic fixtures or appliances. 46thly, the cost of upgrading the grounding system should be factored into the overall cost of the electrical service upgrade. This includes the cost of materials, labor, and any necessary testing or inspections. 47thly, always prioritize safety when working with electrical systems. Never attempt to work on electrical equipment without proper training and safety precautions. 48thly, understanding the difference between grounding and bonding is essential for designing and installing effective electrical systems. Grounding provides a path for fault current to return to the source, while bonding ensures that all metal parts are at the same potential, minimizing the risk of electrical shock. 49thly, when replacing electrical equipment, it's important to ensure that the new equipment is properly grounded and bonded. This may involve upgrading the grounding system to meet the requirements of the new equipment. 50thly, staying informed about the latest advancements in grounding and bonding technology is crucial for electricians. This includes new materials, techniques, and equipment that can improve the safety and reliability of electrical systems.